Welcome to 3D Time, from transportation to physics. My name is Ralph Gilman, and this is Part 6, Orbits. We'll look at orbits and rotations together. There are two pairs of numbers in space and time. The circumference, we'll call it S, and the radius R, and then the period T, and by implication there is a period radius we'll call Q. So the circle is composed of a circumference and a radius. The circumference divided by the radius is 2 pi, or an angle theta is equal to a small part of that arc divided by the radius. A cycle, the time view, we can infer a period radius Q as the period divided by 2 pi. So we can turn that around and we have 2 pi equals time period T over Q, the period radius. And then the period angle, we'll call it phi, is a part of that period divided by Q. Let's look at orbits in space. We have linear speed as defined before. V is the change in s, or length, divided by the change in time. And in this case, that would be equal to the circumference divided by the time period for each cycle of the orbit. The frequency f is defined as the inverse of the time period, and if s is equivalent to 1, then the frequency and the linear speed are equal. The angular velocity omega, that looks like w, is defined as the change in angle divided by the change in time. And if the radius is equivalent to 1, then the linear speed equals the angular velocity. The units are meters per second, revolutions per minute, cycles per second, or hertz. Now the independent variable here is time, and so the dependent variable is an angle in space. Now let's look at orbits in time. The linear pace is defined as before, as u equals the change in time per unit length. And in this case, that equals the period of time divided by the circumference. We'll define a new word, circency, similar to frequency, h as the inverse of the circumference. Now if t, the time period, equals 1, then you can see that the linear pace and the circency are equal. Define the angular legerity, psi, as the change in phi, which is the time angle divided by the unit length. And if the period radius q is equivalent to 1, then the linear pace and the legerity are equal. The units here are seconds per meter, or what we might call circuits per kilometer. And the independent variable here is length. So the dependent variable is the angle in time. So we see that space and time are exactly parallel. Let's look at this new concept of circency. It's the number of circuits per unit distance. So say Alice has a 2-kilometer commute. Then each day her circency is half of a circuit per kilometer. Or if we look at her weekly commute as 1 circuit, then her weekly circency is 1/10 of a circuit per kilometer. Then say Bart has a 10-kilometer commute. Well, then each day his circency is 1/10 of a circuit per kilometer. So we could say that Alice's weekly circency equals Bart's daily circency. Now let's look at the acceleration and expedience. The tangential velocity is like the linear speed we were looking at before, and the tangential legerity is like the linear pace we were just looking at. The centripetal acceleration is defined, centripetal means toward the center, as a, which is the change in velocity per time, which is the time period. And when you expand that out to the circle of 2 pi, the velocity divided by time, that equals the velocity squared over the radius, a famous equation. Now we can also define the centrifugal expedience going the opposite direction. B is the change in tangential legerity divided by the circumference. And again, expanding that, we have 2 pi u divided by s, the circumference, or u squared over q, the period radius. Let's consider circular orbits in space. Assume 3 propositions. 1. Each planet orbits the Sun in a circular path with a radius r and, by implication, a circumference s. The Sun is at the center of mass of each planet's orbit, and the speed of each planet is constant. So recall the centripetal acceleration, a equals v squared over r. Now if we eliminate v from this equation, we find that a is proportional to the radius divided by the time period squared. Now if we bring in something from Kepler's third law about the semi-major axis, which is a because it's an ellipse, but we're going to use this for a circle, so we'll call it r, is related as the time period square is proportional to the radius cubed. If we combine these two equations, we have that the acceleration is proportional to the inverse of the radius squared. And this is an inverse square law in space. If we recall from Newton's second law, we can turn the acceleration into a force with the mass. So the force is proportional to the mass divided by the radius squared. And then from Newton's third law, there's an equal and opposite force proportional to another mass, the mass of the Sun squared. And if we combine these two, we find that the force is proportional to the product of the two masses divided by r squared, or we can include a constant factor, g, we'll call it the gravitational constant, times the masses and divided by the radius squared. This is Newton's force of gravitation. Now we need to switch reference frames. On the left, we have an illustration of 3D space. The Sun is at the focus of an elliptical orbit of the Earth. And at the right, we show the Earth at the focus of a seemingly elliptical orbit of the Sun. This is the way the Sun looks from the Earth. This is a picture in 3D time. It doesn't look this way in space, but it does look this way in time. Now let's consider circular orbits in time. We're going to exchange space and time variables. So we'll assume 3 opposite propositions. 1. The Sun orbits each planet in a circular 3D time path with period t and period radius q. Each planet is at the center of mass of their orbit. 3. The pace of the Sun is constant. So we're looking at orbits in time. Now the centripetal expedience b is equal to the legerity squared divided by the time radius. Or in other words, b is proportional to q over s squared, the circumference squared, which can be stated as b is proportional to the period divided by the circumference squared. Now, if we look at Kepler's third law for 3D time, then the period semi-major axis, which would be c, is q in this case, and is related as the s squared is proportional to q cubed. The circumference squared is proportional to the time radius cubed, or s squared is proportional to t3, the period cubed. Now, if we combine this information, we have that b is proportional to 1 over the period squared. So we have another inverse square law, this time for 3D time. Continuing with orbits in time, we have from Newton's second law for 3D time that the rush is equal to the vast times the expedience, and this is proportional to the vast divided by the period square. Then from Newton's third law for 3D time, we have an equal and opposite rush is equal to the opposite vast times the expedience, and this is proportional to the opposite vast divided by the period squared. If you combine these two, we have that the rush is proportional to the product of the vases divided by the period squared. Or if we use a constant L, we have that the rush is equal to L times the product of the vases over t squared. In other words, the rush of levitation, similar to the force of gravitation, but the direction is toward the smaller body. In conclusion, then, what we have done is to exchange space and time variables. We looked at orbits and rotations, in particular circular orbits, and we found the inverse square law, the law of gravitation, as well as a law of levitation. Next up is part 7, relativity.